Hello, and welcome to our webinar today, AWS Transit Gateway Reference Architectures for Many VPCs. I'm James Devine, a Senior Specialist Solutions Architect. We'll be going through the webinar with you today. So we do have this slated as a 300-level webinar, but certainly don't let that scare you away. We'll make sure that we cover all of the core concepts and dive in deep, but we'll make sure that there's that basic understanding of a concept before we go too far down the rabbit hole. So we'll start off with talking about different VPC connectivity paradigms and how that's changed over the years and how we've added more functionality and features. We'll then dive into Transit Gateway, one of the products we launched at reInvent last year. We'll then talk about Transit Gateway data flows and how that works and how you can segment your networks and do some pretty interesting things right out of the box. And then we'll go into some Transit Gateway reference architectures, how you can take these core concepts and build some really complicated and interesting data flows and really improve the way you're designing your traffic today. So to start out with, we see our customers ask us to help them solve a common set of requirements. So they want to interconnect VPCs within the cloud, certainly, and with their on-prem environment. So just as best practice, having a separate blast radius and making sure your VPCs live within your accounts and separating out workloads. We see very common design patterns there, and customers certainly want to do that and do more and more of that as they grow and scale their business and infrastructure on the cloud. They also want to globally scale out connectivity across regions. So we've been making it increasingly easier to build out your global infrastructure and leverage multiple regions and interconnect them together. And that's certainly become a growing requirement. But with all of this, there's also the paradox of simplifying network configuration. So as you can think through, doing more and more VPCs and more on-prem environments and scaling out globally, how do we simplify that and make it easier? And that's one of the things that we certainly try to do here at Amazon. So that doesn't come without its own challenges. So there's complex point-to-point peering. That doesn't really scale. And we'll get into some of those details and ways around that. But just doing point-to-point connections has its practical limits. There's also some bandwidth limitations on VPN and the overhead of doing an IPsec tunnel. And we'll talk through more of that throughout the presentation as well. And then having the monitoring and management of routing configuration is difficult within a VPC, let alone having many VPCs connected into an on-prem environment. So very common challenges that we know that our customers are facing, and we like to help them solve, and we innovate all the time, and we listen to our customer needs. And that's really led us to come to a different connectivity paradigms, and we'll step through some of those in this presentation and then lead up to Transit Gateway. For VPC peering, this is probably one of our technologies that's been around the longest for connecting VPCs. It's a point-to-point connection between VPCs, and recently we've added that to be in any region. So you can have this global infrastructure and interconnect your VPCs, which works really great. And it is fairly simple to set up between two VPCs. We just modify a route table on both VPCs and point the target at the peering connection. And we can have up to 50 peering connections within a VPC, and that can easily be increased to up to 125. Where this starts to break down and become more complicated is when we want to connect a lot of VPCs. So in this simple example, doing two VPCs, pretty straightforward, and this scales out fairly well. Now let's say we want to add in a third VPC. We now have to add in 2 more peering connections, and we also have to update the route table on all 3 VPCs. So for a small number of VPCs, this becomes, it's easy to set that up and modify those route tables. At scale, this becomes pretty complicated. If you're talking 50, 100 VPCs that you want to connect together through peering, it just becomes increasingly difficult to manage. And with every new connection, you need to connect to every other VPC. So it just grows exponentially with the number of peering connections you need to have. So certainly a great solution, and customers are using it day in and day out, but it does have its practical scaling limits and a bit of a management overhead of deploying it at a large scale. Some of these limits actually brought us to come up with a design that we call Transit VPC. And this has been around for a few years. So we take the same type of router you know and love in your on-prem environment, and we run it in an EC2 instance. And we call this VPC a transit VPC. So in this instance, in the middle here, we have two of them up and running, and they would be typically deployed in different availability zones. So we have high availability between our routers, and if one fails or we need to do an upgrade or maintenance on the router, we have that ability to fail over and maintain our traffic and not lose any connections that are up and going. This is certainly more scalable than doing point-to-point VPC peering. This can scale to tens of hundreds and even thousands of VPCs. It also simplifies our on-premise connectivity because we just connect into that same transit VPC from on-premise. And underpinning all of this over these VPN tunnels that we're running is BGP. So we're able to exchange those routes and have a simplified single view of our network. And then we also get to take advantage of the native capabilities of those router instances that we're running. So for example, if it's Cisco, we could do things like DVMPN and really scale out our infrastructure and add new capabilities. SD-WAN is another thing that customers are starting to integrate into this type of transit VPC architecture. So it gives you a lot of capability and functionality, but it can be complicated to manage and scale. There's also some practical limits of running a router in an EC2 instance. So there's bandwidth limits, there's packets per second limits, and just the practicalities of the whatever you get with running an EC2 instance. And it can start to fall apart at some point. We also have another function called VPC Sharing. This was also announced at re:Invent last year. This is kind of an interesting concept. So historically, a VPC lived within a single account and subnets lived within a single account. With the VPC sharing feature, we added the ability to take that subnet within that VPC and share it with another account within the same region. So in this example here, we might have a public and private subnet in two different availability zones, and then we have subnets for production and development in the same VPC, and these live in different accounts. So we do have that segregation of control where the control is and the provisioning of instances is managed within that individual account, but the connectivity and that VPC is managed centrally within the single VPC. So this does kind of blur the lines between blast radius and some of the interdependencies that we've typically haven't had to worry about in the past. We certainly would recommend, for this type of infrastructure, that you have separate subnets for, in this example, for production and development. That way you can help obfuscate some of those interdependencies that you're building into your VPC stack. For example, if you were to launch a Lambda function in a subnet and that subnet was shared between your development and production environment, you could easily exhaust IP ranges and your dev account could have a detrimental impact on your production account. So we'd certainly want you to think through those type of infrastructures and use cases when you deploy something like this. But from a practical perspective, it's quite scalable. You can share up to 100 accounts per subnet, and 100 subnets can be shared with an account. From a centralized connectivity model, we have a virtual private gateway on our VPC. So our connectivity back to on-premise is just as it typically always would be. And we can have a VPN connection, have a direct connect connection, and we don't need to do that to multiple VPCs. So we essentially have one VPC. Also, other things like DNS, we have a global view of DNS within that VPC, so we don't need to go and do hybrid DNS or anything like that because everything lives within the same VPC. That said, being within the same VPC, we have the implicit route, so everything can route to everything and has layer 3 connectivity. So you can imagine, especially in this example, trying to put development and production in the same environment, they'd certainly be able to route to each other. There's no way to stop that. We need to leverage NACLs and security groups to limit that traffic. And that's a typical best practice, to make sure that you're using NACLs and security groups and having that defense in depth to make sure that traffic only flows where you want it to. With that said, we also introduced Transit Gateway at re:Invent last year, and this was one of our most desired features. So we took the traditional transit VPC and really thought hard about how we could make that a native service that our customers could leverage and not need to go and spin up routers in an EC2 instance and do some of these kind of heavy lifting to make things work the way that they wanted them to, and to be able to have that routing at scale. Some of the key features and benefits of Transit Gateway is it provides centralized routing policies across VPCs and an on-premise environment. It can scale up to support thousands of VPCs across multiple accounts. So out of box, it goes 1 to thousands of VPCs, and you're not having to do anything on the back end. It's all managed by AWS as a service. It also has increased connectivity throughput with multiple VPN connections. There's a lot of really unique things that we built into Transit Gateway that we really can't do with any of the other paradigms that we've talked about previously. There's flexible segmentation and routing rules, very similar to what you'd get with your Transit VPC architecture. It's horizontally scalable, so it automatically scales up and down as you'd expect any AWS service to, and it provides simplified management. We're not having to deploy routers, worry about updating that router code, and all of those type of management tasks, which can be quite time-consuming, and also can result in scheduled maintenance. There's no scheduled maintenance with Transit Gateway. It's just a native service. So if we dig in and look at an overview here, Transit Gateway is a regional router, so exactly like you'd expect with a Transit VPC type of architecture. So it centralizes VPN and AWS Direct Connect. So we deploy a Transit Gateway within a region. This is an important concept. There's some customers that have asked if Transit Gateway goes across regions or if it can connect to VPCs in different regions. It is a regional service. But within that region, it's highly available throughout availability zones. So we can connect thousands of VPCs across accounts. We can also spread traffic across many VPN connections. So it's super scalable and can provide lots of throughput. Within each VPC, we connect it into the Transit Gateway, and we call that an attachment, and we'll get into that a little bit deeper later. So each of these attachments can go up to 50 gigabits a second. So we get a really high throughput connection into this Transit Gateway just out of the gate from doing a simple connection. We also offer flexible routing. So we have the ability to create Transit Gateway route tables. If you're familiar with that traditional routing architecture, it would be more of like a VRF, a virtual routing and forwarding, or what would traditionally be called a routing domain, to put that into the perspective of terms that might be more familiar. So we do offer that level of flexibility and control. And this lets you do some really interesting segmentation and sharing of routes in ways that are difficult or even not possible with other types of networking architectures. And then we also have the VPN and direct connect capability to connect into our Transit Gateway. So if we dig deeper on attachments, there's three main types of attachments. The first of which is a VPC, a virtual private cloud. The way this works is we deploy ENIs, elastic network interfaces. So when you go through the console and you do an attachment to a VPC, we let you select the availability zones that you'd like to use. And the best practice would be to deploy an ENI in every availability zone that you have a subnet in. So there's a drop down, and it'll let you pick which subnet and which availability zone you want to connect. So you want to choose one for each. There's no additional cost for doing that, for doing multiple availability zones. And it's certainly recommended for high availability and throughput. And the same goes across when we connect multiple VPCs. We can see here if we're using 2 availability zones, like the first 2 VPCs, we have that connected with an ENI in each. In this third one, we have 3 availability zones, so we have 3 ENIs, driving home that point of having that ENI in that availability zone. We also have a VPN attachment. And the VPN attachment works very similar to the way site-to-site VPN works today. It's actually the same console. If you're familiar with going and provisioning a VPN connection today, and you've done that and connected it to a virtual private gateway, same type of workflow, but instead of connecting it to a virtual private gateway, we're connecting it into a Transit Gateway. We're also able to do eCMP across these VPN connections, which is pretty exciting. So historically, it's only been 1.25 gigabits a second into a virtual private cloud through a virtual private gateway. So this certainly allows us to scale our traffic way more than we could have previously with just going through a single VPC. We also have the ability to do direct connect. And with that, we can do a 1 or 10 gigabit connection into our Transit Gateway but we could also do a link aggregation control protocol and go upwards of 40 gigabits a second. So again, super high bandwidth connectivity into this transit gateway between our VPCs, and certainly scalable and highly available. If we look at the VPN attachment type, so this is, again, we do the ECMP support. So that allows us to aggregate that bandwidth and have greater availability and throughput. So if a link were to go down, we'd be able to shift that traffic over to another link. Certainly want to make sure that you're thinking through your data flows. Data flows obviously can't be over that 1.25 gigabits as you scale out and aggregate that traffic. So want to make sure that you're thinking through those data flows and how much throughput you need to your on-prem environment or from your on-prem environment into your VPC. That ECMP is also subject to your on-premise customer gateway capabilities, and your customer gateway is just your on-premise routing equipment or your VPN concentrator, wherever you're terminating these VPN connections. There's some vendors that will support up to 4 tunnels in a VPN attachment that'll do ECMP. Others go up to 8. So you really want to check with your on-premise equipment manufacturer to make sure what those limits are and what their support is for EMCP. On the AWS side, the good news is we'll go up and scale as many ECMP connections as you can support, your on-prem equipment can support. So 20, 40, easily doable out of the box as long as your on-premise equipment can support that. We'll natively support that and aggregate that throughput. A new feature that we added recently was Direct Connect support for Transit Gateway. And this was a big ask from our customers. They're used to connecting into AWS with high throughput and low latency. And we certainly wanted to extend that functionality into Transit Gateway and have that be more native than going out over a VPN, over Direct Connect or something like that. So what we're able to do is create a new type of virtual interface. It's called a transit virtual interface. Important point to note here is it's only available on 1 or 10 gigabit a second connections. So if you have a connection that's lower than 1 gigabit a second, this native attachment won't work. You won't be able to go in and provision this transit virtual interface, transit VIV. Also important to note, so if you already have a 1 or 10 gig connection today and you're leveraging 50 virtual interfaces, we actually added a +1 for this transit VIV. So you can actually have 51 virtual interfaces now. We didn't want to limit the ability of our existing customers who are maxed out and want to migrate over to Transit Gateway. So we add that functionality. You can actually still create that transit virtual interface today, even if you're at that 50 limit. So we added that scalability and migration path for you today. And the way that this integrates is through a Direct Connect gateway, and we'll get into that. So Direct Connect gateway, if you're not familiar, is our ability to take what's historically been a private virtual interface and connect into multiple VPCs. So we use that same core capability to integrate Direct Connect into Transit Gateway. So we can see on this diagram, we have our on-premise equipment. We've provisioned a transit virtual interface on our Direct Connect, and that connects into our Direct Connect gateway. This gives us the ability to then connect to globally transit gateways across the world. Now, there's a growing list of supported regions that support Direct Connect Gateway and Transit Gateway. Certainly see our public documentation to make sure your regions are there. And of course, in the fullness of time, we'd like it everywhere. And that's something our service team is rapidly trying to get out the door and expand globally to each and every region that we can. So with this Direct Connect Gateway, we can connect into up to 3 transit gateways. So we can build out a global connectivity between our VPCs and our on-prem environment. And in this example, you see we have US East 1, US West 2, and EU West 1. We're able to do that globally and connect in, and this can be tens of thousands of VPCs across these regions. So really scalable and a good way to aggregate all that connectivity into our on-prem environment. Some important things to note here before you go down and start implementing this. We do have, we allow 20 prefixes per transit gateway to the on-prem environment. So certainly plan through that. So you could do route summarization, always easier said than done. There is going to be some IP planning and some thought that goes into this to make sure that you can fit within these limits and make sure that you can have this connectivity to your on-prem. Even if especially if you have like 1,000 VPCs that you're connecting into a transit gateway, you might not be possible within that 20 prefix construct. So there might need to be some planning done there, and certainly think through that and how you would do that. But it's 20 prefixes per transit gateway that we can advertise to Direct Connect Gateway to on-premise. From on-premise, we can advertise 100 prefixes to Direct Connect Gateway, and those will be propagated to each of the TGW route tables, the Transit Gateway. So we have that flexibility both ways between the number of routes that we can advertise. A nice thing here, since we've leveraged the Direct Connect Gateway construct, is for high availability, we can simply provision another transit virtual interface and connect it into our Direct Connect Gateway. And now we have high availability. An important note here is you're only allowed to have one transit virtual interface per Direct Connect connection. So this would require 2 Direct Connect connections, but you need to do that for high availability anyway. You'd want to use a diverse provider going through a different path, potentially even to a different region. So you get that level of high availability, and then we're able to extend that to the Direct Connect Gateway and have our end-to-end connectivity. We could also do traffic engineering here. We might want some traffic to go over one transit VIF and not over another. And we do that through either AS prepending or BGP communities in our on-prem advertisements to the Direct Connect Gateway. So we have that ability to influence traffic and how it flows across our network. The advantage of Direct Connect Gateway as well is it gives us a multi-site capability. So in this example, we have an on-prem environment in the US, and we also have an on-prem environment in Ireland. And we're able to provision a transit VIF on each of those connections and connect into the same Direct Connect Gateway. So we can advertise, obviously, our local IP space for that specific on-prem environment, but we also have the ability to, on the back end, do some traffic engineering. So say we had some type of MPLS connectivity or some type of private fiber between these on-prem locations, we can actually fail over and provide high availability on your edge of the on-prem network if there were ever a failure or disruption in one of those transit virtual interfaces. So it's a great way to be able to have that. You just advertise out using AS path prepending or BGP communities, the other region, and make it less preferable. So if that more preferable region were to go offline, then traffic would flow through the other region that's still online. So another great capability and a good reason that we've integrated with Direct Connect Gateway. Another core concept with Transit Gateway is route tables. And again, the easiest way to think of these is like a VRF or routing domain in your traditional type of router. So this can control routing between different types of attachments, be it the VPC, the VPN, or Direct Connect. We allow up to 20 route tables per Transit Gateway. We can upscale this and increase that to 40 pretty easily. But a word of caution there, most of the architectures we're seeing customers implement, the vast majority, 20 route tables, is far more than enough than they need. If you're pushing that and thinking that you might need more, I would definitely recommend consulting with us and talking through what that looks like and seeing what we can do there. We also have the ability to create black hole routes. So we can take traffic and at scale, just drop it once it hits Transit Gateway. So that adds an extra layer of security and control that a lot of customers that I've talked about that are really happy with just being able to take certain routes and say, well, you know what, this is a production environment. I'm on in a dev VPC. I just want to block all of that traffic. And we can do that natively within the route table by adding a black hole route. So as we're talking about routing and route tables, it's important to talk about the behavior of the path selection on Transit Gateway. So we're always going to prefer the most specific route, the route with the longest prefix match. We then prefer static route entries, including site-to-site VPN routes. We'll then prefer VPC propagated routes, and then BGP routes propagated from Direct Connect Gateway, and then BGP routes propagated through AWS site-to-site VPN. Important note here is you're thinking through this hierarchy of how routing is determined. You want to make sure that you're planning appropriately. So you could come into a situation where you have a static VPN into your Transit Gateway and a BGP propagated dynamic connection, and we prefer that static one. And that might not be the behavior that you prefer. So certainly think through these, how you architect out your route tables and how you add those routes in. And at the end of the day, you can always add in a more specific route, and that's one way that customers can guarantee that traffic is flowing the way that they'd like to. And we do provide that ability to, even if you have these BGP and static routes, you can still put in specific routes and have static routes that you place on the route table yourself. so you have a lot of control. Another point here is on ASNs, autonomous system numbers. So we use private ASNs for Transit Gateway, Direct Connect Gateway, and VPNs. So each transit gateway that you create within a region or globally, we would really encourage you to use unique ASNs, especially you might not want to interconnect them now, or you might not have the capability to do so. But when we do have that capability, or if you suddenly down the road need to start connecting together transit gateways, it's nice to have that advanced planning where you're using unique ASNs. And another important point here is as you launch the console, you could go in region by region and create transit gateways. And if you just accept the defaults, they'll actually have the same ASN. So certainly want to make sure that you're aware of that and designing that from the get-go to make sure that you have that flexibility and expandability in the future, because you can't change the ASN on that after you've provisioned a transit gateway. Also, the Direct Connect Gateway and the Transit Gateway also require unique ASNs. And again, if you go through the console and create a Direct Connect Gateway and create a Transit Gateway, you'll quickly find that they have the same ASN, and when you try to connect them together, it won't work. So you want to make sure that you're planning through this because that could be an operational issue if you put a Transit Gateway into production and then have a Direct Connect Gateway into production and then have them to connect to each other, and they just won't. So certainly make sure that you're planning through these ASNs as you're designing and implementing your connectivity, especially hybrid connectivity to on-prem and between transit gateways. Another notion that we have in Transit Gateway is propagations. So if you're familiar with the way VPNs and Direct Connect work today and how you connect them into a VPC, we can take those routes learned over BGP or even statically and propagate them into the VPC route table. So we've extended that same type of notion, and we can propagate routes that are connected. When you do an attachment, we can propagate those routes into the Transit Gateway route table. So this important note here, that's different than the VPC route table. There's still a separate VPC route table, and we can't currently propagate routes to that VPC route table. The good news there is we can use a default route, and you can see that on the screenshot on the bottom left. We have a default route that just points to the Transit Gateway. So we have that ability to simply connect in, and even as we add more routes to that Transit Gateway, since it's the default route, we don't need to go in and update that VPC route table in the future. It just will work. We also, on this top right here, we can see when we deploy our Transit Gateway, we have a few options that control how things are propagated and how route tables are associated. So I wanted to call that out too. You don't get the opportunity to change that after you've deployed a Transit Gateway, so it's important to think through that beforehand. So the default route table association will actually create a default route table, and we'll get into that in some of the next slides. If you enable that, it works great for just out-of-box connectivity. You might want to consider disabling that so you can have more fine-grained control over route tables, and there's an automatic routing when you do an association. Also, by default, will take the attachment and propagate the route table with that attachment. You can disable that functionality here as well. If you want more fine-grained control over how your routing works and how you're doing that route propagation, then certainly disable this, but it would be enabled by default. So hopefully that was a good overview of how Transit Gateway works between attachments, propagations, and the different types of ways you can leverage Transit Gateway. We're now going to get into some of the data flows. So taking these constructs and take a look and dive deep into how that traffic flows across the network. So by default, if you want just a flat network, so certainly choose all the defaults when you launch the Transit Gateway. We'll go ahead and attach a VPN, or a VPC here, and we'll see we have an ENI in each availability zone as per best practice. And we'll see that that route will get propagated to the default route table on that Transit Gateway. Per VPC, here I'm just doing a 10.0.0.0/8, and I'm pointing that at the Direct Connect at the Transit Gateway. I can then go in and connect additional VPCs, and we can see as I attach these VPCs to the Transit Gateway, that default route table is getting updated with these routes. So that's that propagation feature that we covered. So they're getting propagated with each. And again, this route here will, as I add more attachments, within my VPC, this will allow that traffic to point to the Transit Gateway route table. So an important point here, this could, again, in the previous example, this could just be a default route if I wanted to also have internet traffic flow across here. So pretty simple way to scale and build. And each of these attachments will give me 50 gigabits a second. Then here I can see the propagation. I have full connectivity here, so everything can talk to everyone. They're all essentially in the same routing domain. They're in the same route table here, so they can all speak with each other. Again, subject to NACLs and security groups, which you'd additionally want to implement. Now, I could extend this one step further and say I wanted a segmented network. So in this example, I don't want any of my VPCs to be able to talk to each other, but I would like them to talk to an on-prem environment. So I'm going to go ahead and create a default route to the Transit Gateway. I then have a separate route table for my VPN. The route table for my VPCs, I'm going to have a default route that points to the VPN as the destination. I then have a route table on my VPN connection, and that will have the attachment as a destination for each of the CIDRs for the VPCs, which will allow traffic coming from the VPN to flow into the appropriate VPC. So I can see this default route here allows all that traffic. We're just pushing everything to the Transit Gateway. Then from the Transit Gateway, we're pushing all of that just over the VPN, so I can have on-prem internet and other things and do centralized filtering and monitoring of all my traffic through the on-prem environment. And then the return traffic hits this route table for the VPN, and I have that end-to-end connectivity. What's important here is I have no east-west connectivity, so I've essentially segregated each and every of my VPCs, but I then have full north-south connectivity to and from my VPCs into the VPN connection to my on-prem environment. So hopefully those two give you a sense of how we can start to build some routing and segregate traffic out within our network. Building on that, we're going to talk about some reference architectures now and dive into different ways that we'd integrate this and have some more complicated routing. So this is our overall reference network architecture. If you saw our reInvent session last year, you should look intimately familiar. We'll talk through a few pieces of this. So we have outbound connectivity, and it's separate VPC. So we're able to do things like URL filtering. We can do NAT gateway. We can do DLP and proxying for all of that outbound connectivity. We can do edge services. We could do WAF, SD-WAN, VPN, and control that traffic into our transit gateway. And we could also do inline services. So this is kind of interesting here, being able to do firewalling, putting in a next-gen firewall, doing IDS, IPS, and we can inspect east-west and north-south traffic, which is pretty powerful because this becomes much more difficult to do without something like a transit gateway in the mix to facilitate this type of connectivity and routing of traffic. So digging into this type of architecture, we'll talk about a centralized NAT solution. So in this architecture, we have two VPCs at the top left. We don't want them to talk to each other, so we have a black hole route here, so they can't speak with each other. Then we have a default route that in that VPC route table that allows it to go to the VPC outbound attachment. We then have an outbound route table that has the CIDR of each of our VPCs that direct it to the VPC attachment. We then connect in our outbound VPC. This has a CIDR of its own. Important to note here, we have separate route tables for the ENIs that connect into the transit gateway and for our appliances. For our appliances, they have obviously a default route out to the IGW, so they can route out to the internet. And then they have a default route back into the transit, or a VPC route for 10.0.0.0/8 into our transit gateway, so they can route back into transit gateway and return that traffic. Important to note here, we also need a special route table for each of our ENIs, so they can route their default route into an ENI, and that ENI is the ENI of that either NAT gateway if it's running our NAT gateway service, or into whatever third-party vendor you're running for NAT. So that allows that traffic, once it leaves transit gateway and enters into the VPC, to be directed into our appliance. So if we look here, our spoke VPCs have a default route out to the transit gateway. We're just pushing all traffic out there. We then have a default route on our VPC route table, and this is pointing all of our traffic at our outbound attached VPC. And then we have a route here. Once it hits that ENI, we'll point it at the appropriate firewall or NAT gateway appliance. From there, it has a default route out to the IGW. Important note here is we are doing SNAT because obviously these are all private IP addresses, so we're source NATing so it can go out to the internet, which would be a public IP address. So we're managing that and having that flow symmetry when flows come in and out and talk out to the internet. Another thing to note in this type of architecture is we can only have one ENI per availability zone. Ergo, we can only have one firewall or NAT gateway per availability zone as well. So there are some scaling things here. Also, as you plan for high availability in this type of architecture, you're going to want some type of Lambda function or some way to monitor the health of those backend appliances. So if there were an issue, you can update the route table and have an ENI point to another appliance and then bring a healthy appliance online. So there is some additional work you need to do here. Certainly, if you're using a third-party vendor, you'd want to consult with them and make sure that you're adhering to their best practice for implementing this, and certainly thinking through how your high availability is working in this type of architecture. Then we can see we have the default route back here into our transit gateway, which would hit the attachment on the return. And actually, we'd black hole this type of traffic if it's VPC to VPC. Another thing here, because we are running a NAT instance in a fleet of NAT, it is possible to have VPC to VPC traffic because the firewalls know how to get to both of those VPCs. So here we're explicitly black holing it so we don't have that VPC to VPC traffic. Obviously, this would need to be required if you wanted to be able to have that traffic flow from VPC to VPC. Another way to kind of alleviate some of those things that we talked about in those concerns around scaling and availability is doing a VPN attachment. So in this architecture, we're not actually attaching to the transit gateway through direct VPC attachments with ENIs. We're doing it through a VPN connection. So we have our appliances up in the right, and we're doing a VPN tunnel back to the transit gateway. And here it looks fairly similar to before, where we have our VPC route table with a default route out to our outbound VPC, but this time it's to a VPN, not to that VPC connection. And then we're still black holing traffic, so we don't have connectivity between VPC A and VPC B. We're also doing ECMP across these connections, so we can scale that out horizontally, add more appliances, and get more throughput and bandwidth if we need to, and also scale it back in if we, maybe it's an odd hour of the morning and we don't really need that much egress traffic. We can scale that in and cost optimize. So here we add in another one and we can scale that in and out. So what this traffic flow looks like, we have the default route on our transit gateway, which points the traffic to the transit gateway, and that hits the VPC route table, which has that default route out to the VPC VPN. From there, we go to the egress VPC. That has a default route out to our NAT gateway, out to an IGW, out to the internet. For the return traffic, the egress VPC will hit the outbound VPC route table, and we'll see we have that CIDR as a direct attachment. And then we're able to have that traffic flow back into the VPC. So certainly a more scalable and can add more flexibility in your implementation. Also note here, we're still doing source NATing because we're going out from private IP to public IPs. And also we want to be able to maintain flow symmetry. So we want to make sure that we're always doing that source NATing. It is possible that a packet could flow out to one appliance and flow back in on another appliance if we weren't doing source NATing. So that source NATing pins that connection to a specific appliance. So definitely something to keep in mind as well. And again, talk to your vendor with what their recommendations are for best practice here to implement their specific solution. Another type of architecture we can use is an edge ingress. So in this type of environment, we want to control all of our ingress traffic into our VPC and maybe put it through a stateful next generation firewall or some type of other appliance or a load balancer that we prefer to use. That's certainly a possibility here for our ingress. So we typically have something like an ELB here, an elastic load balancer. And this is almost like an ELB sandwich type of architecture that we've talked about before and publicly in our documentation, putting an ELB and having firewalls, and then behind those firewalls, we could actually have another load balancer and make sure that we're adding in availability at every step of the way. So the EOB will direct to our instances, and we're actually doing a destination NAT because we're taking the public IP address, which is actually a private IP address by the time it hits the firewall, but we still need to do another layer of NAT on top of that. So we do a destination NAT onto Transit Gateway. So what this looks like is in our edge route table, we have a route for our VPC, and that goes through the attachment on the ingress. On our Transit Gateway traffic for the return traffic on the VPC, we have the CIDR range of that ingress VPC, so the return traffic will go out and hit the Transit Gateway. Then on that VPC route table, we'll take that and it will go out over our VPC VPN Edge. Then from there, we have a default route out to an IGW, and that will route out to an IGW. In this case, the EOB would be in a public subnet, and it would leverage that route to go out into the internet. So we have that hybrid model where we're able to connect in and leverage some of our existing existing technologies for your firewall vendors. You're able to integrate them into the network and have that same type of functionality you'd expect from your on-prem type of environment. Another interesting thing here that we could do is VPC to VPC inspection. We can statefully inspect traffic as it's flowing from one VPC to the other VPC. And the way this works is, again, here we're using ECMP VPN attachments for our centralized inspection VPC. The reason we're doing this is so we have that scalability. We can scale up and down and have more flexibility and high availability than we would with a VPC attachment. Certainly, again, talk to your vendor and see which one they prefer you to support and what their best practice is for implementation. If we look through this data flow here, so in this case, we have the VPC CIDR, which goes to this 10.0.0.8, which goes to the Transit Gateway. That traffic will hit our inline, will hit the VPC to VPC route table, and that just has a default route out to our inline VPC, which is going over a VPN connection. So for that inline route table, for the return traffic, we know that CIDR is associated with that VPC. And then we know that we need to hit the IP address of that VPC, which is connected to the Transit Gateway. And then we have the return traffic, which also hits that default route going to the inline VPC. And we can finally go to attachment B. And we have that end-to-end connectivity. And here we can do stateful inspection. We can put next generation firewalls. We can integrate a lot of the typical type of hardware you do on-prem in a way that there really wasn't all that easy to do before, and a way that's certainly more scalable. Obviously, keep in mind here, each of these VPN connections still is 1.25 gigabits a second. So we are taking that 50 gigabit a second capability of the VPC attachment and essentially moving it down to 1.25. But if that meets the application requirements, we can certainly ECMP and get multiple of those 1.25 gigabit a second connections and scale up as needed. Another important point here is we are doing source NAT between VPCs, and we're doing this for flow affinity. So we want to make sure that we have flow symmetry. The way that these type of stateful inspection devices work is they're stateful. So if I'm sending traffic out from one appliance and it returns to another appliance, that other appliance doesn't have that state and the traffic would just be blocked. So by doing the source NATing, we're able to pin that connection to a specific appliance and ensure that for the life of that connection, it still goes through and is maintained and tracked by that appliance, and we can do our inspections. And we're also running BGP here. So for BGP, we just have a default route to the local IP. We can also do outbound VPC services. So this is good for URL filtering, NAT gateway, data loss prevention. So we kind of dug into the NAT gateway case, but in this, we're able to control our traffic. So here again, we have a default route out to our outbound VPC, and we're doing ECMP VPN across these different appliances. And we have a CIDR for our outbound VPC. Again, here we're applying source netting. So especially if we're going outbound to the internet, we're going to have to do a source net. We can also do this without VPN. Again, this is the typical doing ENI attachments. The same caveats here. You need to really think through your availability and how you're maintaining and withstanding the loss of an appliance or something not going quite as expected or not working. So there's things you can do with Lambda again and other types of methodologies to make sure that traffic is available and doesn't get dropped. And you certainly don't want to create a single point of failure. And again, here just driving home that the route table for each of these ENIs or for each of the Transit Gateway ENIs that we place within the VPC has its own separate route table, and that route table default routes to the ENI of our appliance. So that's how we get that end-to-end traffic flow from the Transit Gateway into our appliance running within that VPC with its own specific route table. And again, that would either have a default route out to an IGW or for the return traffic have a route out to the Transit Gateway for the VPC siders. We also have the ability to connect to Transit Gateways in multiple regions. So as it stands today, this isn't a native functionality that we have, but we can certainly do it with VPN. So if we take our tried and true Transit VPC, we can put one of those into the environment, and we can do VPN connections from instances and appliances within that Transit VPC. So they're able to receive the routes from a Transit Gateway in one region, do BGP and advertise those routes back out to a Transit Gateway in another region, and vice versa. In the return direction, we have that bidirectional Transit Gateway exchanging routes between each other through BGP. So we have connectivity end to end, and VPCs can talk to each other. Unfortunately, we do need to introduce a Transit Gateway into this architecture, and same standard caveats apply with that and VPN. Certainly something to think through. This is great for customers today that do need to talk to two Transit Gateways between regions. Certainly not a capability we have now. But the good news here is, as we announced at re:Invent last year, we do have plan to support inter-region peering for Transit Gateways, and that's something that should be coming soon. Our service teams are actively working on that because we hear this from a lot of customers. They really want this capability to natively be able to do an attachment from a Transit Gateway in one region to a Transit Gateway in another region. And we'll be doing this through our inter-region VPC peering. So essentially just peering from Transit Gateway to Transit Gateway using already native functionality that we have. And this will be hopefully coming out soon. Another type of architecture here that I'm kind of running a long time, I'll kind of go through quickly so we can get to our Q&A. So we also have the ability to centralize PrivateLink. So if you're not familiar with PrivateLink, this is the ability to either connect to an AWS native service from within your VPC using private IP space, also the ability to connect to services that you provision behind an NLB within a VPC. So there's charges for these VPC endpoints per hour and per data flow. So customers have asked, how can we centralize this so we don't need to put VPC endpoints in every VPC? Certainly 2 or 3 aren't that bad to scale, but if you have 1,000 VPCs, 1,000 endpoints just for one service can become burdensome. So the good news here is we have the ability to do that today. There are some caveats with DNS, so I'll go through that quickly. We also have a blog post if you're interested in this architecture that was published a few weeks ago. We can certainly track that down and dive more into what that looks like. But essentially, when we create a VPC endpoint here, we'll just disable the private DNS. We'll then create a private hosted zone that has that same service name. And here's a view of what that looks like. For example, here I'm doing SSM, our Simple Systems Manager. So I take that full name, and then I do an alias record, and that alias record points at my VPC endpoint. So this allows me to have that view of DNS within that VPC. On the back end, the reason that we have to disable that DNS option and do this DNS option is that on the back end, we create a private hosted zone that exists in a service VPC that you don't have control over. So this allows us to take that DNS resolution, move it into your VPC in a way that you can control and attach to multiple VPCs. And we do this through private hosted zone associations for VPC to VPC connections. So this allows us to connect to, we can scale up to 1,000 VPCs. If they're in the same account, we can do it through the CLI. If they're in different accounts, we can do it through CLI. If they're in different accounts, do we need the CLI? Natively, you can do it within the same account. We can also extend this connectivity to on-prem. And this is where Route 53 resolver inbound endpoints come in. So from our on-prem environment, we can do a conditional forward and have that traffic flow and have that rule to allow that. And here's what that rule looks like. So we associate a rule with that Route 53 resolver for the name of that PrivateLink endpoint. And then we're able to connect in from on-prem, and our DNS resolution will work. And then we'll be able to connect to that endpoint and privately access a public AWS service. So a pretty unique architecture and something customers have been asking about. So certainly, I'd recommend to go and read the blog post if you're interested in this. And we can certainly talk more through that. So hopefully you found this webinar useful and kind of left with some thoughts about how you can do things and how you can interconnect your VPCs. There's a number of ways to interconnect your VPCs on AWS and to and from your on-prem environment, not limited to peering, Transit Gateway, Transit VPC, VPC Sharing, and probably some more that I'm leaving out. So the point I wanted to really drive home here is there's no right way. So there's a way that works for you, and given your requirements, it will vary very greatly. So if you don't need inline inspection and you have 2 VPCs, that looks different than if you want inline inspection and you have 1,000 VPCs. So certainly think through that and your requirements. Transit Gateway is a native AWS service, so it's highly available and scalable and managed by AWS. So this greatly improves on the Transit VPC design pattern, and we've taken a lot of the pain points and the technical debt associated with that and made it a native service. So certainly consider leveraging that. It is fairly simple to migrate, and we have some architectures and blog posts out there on how to migrate from a Transit VPC to a Transit Gateway. So certainly take a look at that and consider that as you think through your architecture. And also a final call out, we're here to help. So certainly talk to your account team. They can talk through and explain these services even more in depth. They can also have the ability to bring in a specialist, so someone like myself that can talk through your architectures and some of these caveats and make sure that you're designing and building in a scalable manner that's cost effective and makes the most sense for your requirements. We really want to make sure that you built this right and do it right the first time and avoid any types of pitfalls with your implementation. So we're certainly here to help, and being a customer-focused company, we're customer-obsessed, and we want to make sure that you're successful in doing things in a good way. With that, we'll open it up to some questions, and so hopefully you've enjoyed the session and certainly willing to dive into any questions that you have. Thanks.